So here's something to think about as you settle in tonight. Take a breath. Feel the weight of the blanket on your chest. Feel the mattress underneath you. Notice the air in the room, the soft sounds of the world outside winding down. Everything around you right now, the pillow under your head, the walls of the room, the floor beneath the bed, the trees outside, the ground those trees are rooted in. All of it is made of atoms, protons, neutrons, electrons, bound together in familiar arrangements. Carbon, oxygen, hydrogen, nitrogen, iron, the stuff of you, the stuff of Earth, the stuff of stars. And here's the thing that should keep you up at night. Except tonight, it's going to ease you to sleep, because mysteries can be strangely comforting when you let them. Everything you've ever seen, every star, every planet, every galaxy, every person, every grain of sand on every beach, all of it, every single thing you have ever looked at, or touched, or experienced in your entire life, makes up roughly 5% of the universe. 5%. That's it. That means 95% of everything that exists is something we have never seen, never touched, never directly detected. And about 27% of that invisible majority is something we call dark matter. We gave it that name not because we understand it, but precisely because we don't. It's dark because it doesn't glow. It's dark because it doesn't reflect light. It's dark because, as far as any instrument we have ever built is concerned, it might as well not be there at all. Except for one thing: it pulls. It has gravity. And that gravity shapes everything. Every galaxy you've ever seen in a photograph, every cluster of galaxies stretching across hundreds of millions of light years, every strand in the vast cosmic web that gives the universe its structure, all of it is held together, sculpted, and cradled by something we cannot see, something that outweighs all the visible matter in the universe by a factor of roughly 5 to 1. You are lying in bed right now, in a body made of atoms, on a planet made of atoms, orbiting a star made of atoms, inside a galaxy that is mostly not made of atoms. Most of your galaxy is made of something else entirely, and nobody knows what it is. That's the mystery, and it's one of the deepest, strangest, most humbling puzzles in all of science. Not because we just noticed it recently. People have been worrying about this for almost a century now. Not because we haven't looked. Some of the most sensitive instruments ever constructed, buried deep underground in abandoned mines and hidden beneath mountains, are specifically designed to catch dark matter in the act. And not because we lack theories. There are dozens of candidates. From exotic particles with names that sound like they belong in a fantasy novel, to entirely new forces of nature we haven't discovered yet. The mystery persists because despite all of that effort, all of that ingenuity, all of those billions of dollars and decades of work, dark matter has never once shown its face. We know it's there. We can see what it does. We can measure its effects with extraordinary precision. But we have never, not even once, caught a single particle of it. Not in a detector, not in a collider, not anywhere. And tonight, I want to take you through that whole story. How we figured out something invisible was out there. Why we're so sure. What it might be made of. Why it's been so impossibly hard to find. And what it would mean. What it would really mean if we finally caught it. It's one of those stories where the more you learn, the stranger it gets, and the more beautiful the questions become. So let's start at the beginning. Not the beginning of dark matter itself. That probably happened in the first fractions of a second after the Big Bang, and we'll get there. Let's start with the beginning of the mystery. The moment someone first looked at the sky and realized the numbers didn't add up. The year was 1933. And the person was Fritz Zwicky. Now, Zwicky is one of those characters in the history of physics that you almost can't believe was real. He was born in Bulgaria to Swiss parents, grew up in Switzerland, and eventually made his way to Caltech in Pasadena, California, where he spent the bulk of his career. And by all accounts, he was brilliant, abrasive, confrontational, and about 40 years ahead of his time on almost everything. He coined the term supernova, the explosive death of a massive star, and predicted that supernovae could be used as distance markers to measure the expansion of the universe, which is exactly what astronomers did in 1998 when they discovered dark energy. He predicted neutron stars, the ultra-dense remnants of collapsed stars, before anyone had found one, at a time when most physicists thought the idea was absurd. He pioneered the concept of gravitational lensing, light being bent by gravity, decades before it was confirmed observationally. He even proposed the idea of using rockets to reshape the solar system, which sounds like science fiction, but was perfectly serious to him. And he was, apparently, absolutely insufferable to work with. He reportedly called his colleagues at Caltech spherical bastards, because, he said, no matter which direction you looked at them from, they were still bastards. He feuded with nearly everyone. He accused fellow astronomer Walter Baade of being a Nazi, which was unfair and untrue. He alienated collaborators with his temper and his stubbornness. But he also had a generous side that rarely gets mentioned. After World War II, he personally organized shipments of scientific books to war-damaged libraries across Europe and Asia. He was complicated, and he was difficult, and he was right about things that mattered, long before anyone else was willing to consider them. That's the kind of guy Fritz Zwicky was. Brilliant, rude, and almost always right before anyone was ready to hear it. In 1933, Zwicky was studying the Coma Cluster, a huge collection of over 1,000 galaxies, about 300 million light-years from Earth. He wanted to know how much mass the cluster contained, and he had two ways to estimate it. The first was to look at how bright the galaxies were, estimate how many stars they contained, and add up all the mass of all those stars. That gives you a number, the visible mass. The second method was more subtle. He measured how fast the individual galaxies were moving within the cluster. If you know how fast things are orbiting, you can work backward and figure out how much gravitational pull is needed to keep them on those orbits. More mass means more gravity, means faster orbits. It's the same principle you use to weigh a star by watching how its planets move, or weigh the Earth by watching the moon. Simple enough. Elegant, even. But when Zwicky compared the two numbers, they didn't match. They didn't even come close. The galaxies in the Coma Cluster were moving way too fast for the amount of visible matter he could see. If the only mass holding the cluster together was the mass of the stars, those galaxies should have been flying apart. The gravitational pull of the visible matter just wasn't strong enough to keep them bound together. There had to be more mass, a lot more mass, hidden somewhere that he couldn't see. He called it Dunkel Materie, dark matter, and his estimate suggested there was about 400 times more dark matter than visible matter. That number turned out to be too high. His instruments and assumptions weren't perfect, but the basic observation was absolutely right. There was far more mass in the universe than what was shining. And here's the thing about Zwicky's discovery. Almost nobody cared, not at first. The astronomical community largely ignored his finding, partly because his methods were rough, and partly because, well, he'd alienated so many of his colleagues that they weren't particularly inclined to take his ideas seriously, and partly because the idea itself was just too weird. The notion that most of the universe was made of something invisible felt, to a lot of people at the time, more like an error in the measurement than a discovery about nature. Surely, they thought, the missing mass would turn up. Maybe there was just a lot of dust. Maybe the faint stars at the edges of galaxies were harder to see than expected. Maybe the calculations were just off, so the idea sat there, mostly ignored, for about 40 years. 4 decades. Imagine being right about something that important and watching the world shrug. But then, in the 1970s, the evidence came flooding back, and this time it was impossible to ignore. The person most responsible for that flood was an astronomer named Vera Rubin, and her story is one of the most important, and for a long time, one of the most under-recognized in all of 20th century science. Rubin had wanted to be an astronomer since she was a girl, lying in bed at night in Washington, D.C., watching the stars wheel past her bedroom window. She built her first telescope at age 14, with her father's help. When she applied to graduate school at Princeton, she was rejected. Princeton's astronomy program didn't admit women. This was 1948. She went to Cornell instead, where she studied under the great physicist Hans Bethe, and then to Georgetown for her doctorate, where she studied under George Gamow, one of the founders of Big Bang cosmology. Despite the quality of her work, she spent years being underestimated, sidelined, and excluded from facilities and collaborations that were open to her male colleagues. When she first visited the Palomar Observatory in California, home to the famous 200-inch Hale telescope, then the largest telescope in the world, there was no women's restroom. She was one of the first women to observe there. She drew a little skirt figure on the men's room door and kept working. Rubin was working at the Carnegie Institution in Washington with her collaborator, Kent Ford, who had built an exceptionally sensitive spectrograph, an instrument that could measure the velocities of stars in distant galaxies by detecting the Doppler shift in their light. And she was measuring something very specific, the rotation curves of spiral galaxies. Here's what that means, and I want to walk through it carefully, because it's one of those things that's simple once you see it, but really important. When you look at a spiral galaxy, picture the classic pinwheel shape, with a bright central bulge of stars and those sweeping spiral arms trailing outward like cream stirred into coffee. The stars closer to the center are orbiting the galactic center, and the stars further out are orbiting the galactic center too, just at a greater distance. The whole thing is spinning, like a cosmic pinwheel, but not the way a solid wheel spins. Each star is on its own independent orbit, held in place by the collective gravitational pull of everything else in the galaxy. Now, if most of the galaxy's mass is concentrated in the bright central region, which is what it looks like, because that's where most of the visible stars are packed together, then you'd expect the outer stars to be moving more slowly than the inner stars. It's exactly the same as our solar system. Mercury, close to the Sun, orbits quickly, about 107,000 miles per hour. Neptune, way out at the edge, orbits at just over 12,000 miles per hour. The further out you go, the weaker the gravitational pull of the central mass, and the slower the orbital speed. This is Kepler's third law, and it works beautifully for the solar system, where almost all the mass is concentrated in the Sun at the center. You'd expect the same pattern in a galaxy: fast orbits near the bright center, slower orbits out at the dim edges. That's what Newtonian gravity predicts, and it's what everyone expected to see. But that's not what Rubin found. When she and her collaborator Kent Ford measured the velocities of stars at different distances from the centers of spiral galaxies, they discovered that the rotation curves were flat. The stars at the outer edges of galaxies were moving just as fast as the stars closer in some cases, even faster. This makes no sense if the only mass in the galaxy is the visible mass. The outer stars are moving so fast that they should be flung outward into intergalactic space. Something has to be holding them in, and that something has to extend far beyond the visible edge of the galaxy. A vast, invisible halo of mass that you can't see, but whose gravitational influence shapes everything. Let me give you a way to feel this in your bones. Imagine you're watching a merry-go-round spinning in a park. The horses near the center are moving at a certain speed. The horses at the edge are moving faster. They have to, because they have more distance to cover in the same amount of time. But now imagine that the horses at the edge are moving much, much faster than they should be. So fast that they should be flying off. The centripetal force just isn't strong enough to hold them on. They should be catapulting off into the park, but they're not. They're staying on the merry-go-round, spinning happily, as if some invisible hand is holding them in place. That's what Rubin saw. Something invisible was holding the outer stars of galaxies in their orbits. Rubin measured galaxy after galaxy after galaxy, and the result was always the same: flat rotation curves. Every spiral galaxy she looked at was behaving as though it was embedded in a massive cocoon of invisible matter that extended well beyond the reach of its visible stars. And unlike Zwicky's work from decades earlier, this couldn't be dismissed as a fluke or a measurement error. The instruments were better. The data was clearer. The pattern was universal. Rubin herself described it beautifully. She said that, in a spiral galaxy, the weights of the stars we can see are like the visible part of an iceberg, just the tip. The vast bulk of the matter lies beneath the surface, unseen, dark, and overwhelming in its dominance. Now, it's worth pausing here to appreciate something. By the mid-70s, the evidence was strong. Galaxies rotated too fast. Clusters of galaxies were bound together too tightly. The mass we could see was nowhere near enough to account for the gravitational effects we could measure. But you might still wonder, how sure can we really be? Maybe our understanding of gravity is wrong at large scales. Maybe Newton's laws or even Einstein's general relativity break down when you're talking about distances of hundreds of thousands of light years. That's a perfectly reasonable objection, and some very smart people have pursued exactly that line of thinking. We'll talk about that later, because it's a fascinating thread in its own right. But for now, let me tell you about some of the other lines of evidence that have piled up over the decades. Because the case for dark matter doesn't rest on galaxy rotation curves alone. It rests on an extraordinary convergence of independent observations, all pointing in the same direction, all saying the same thing. There is far more matter out there than we can see. One of the most beautiful and direct pieces of evidence comes from gravitational lensing. This is something Einstein predicted in his general theory of relativity. The idea that massive objects curve the fabric of spacetime, and when light passes through that curved spacetime, its path bends. Here's a way to picture it. Imagine spacetime as a rubber sheet stretched taut, and a massive object like a galaxy cluster as a bowling ball placed on that sheet. The ball creates a dip, a valley, and anything rolling nearby, including light, follows the curved surface rather than traveling in a straight line. Now, this analogy has its limits. Spacetime isn't actually a rubber sheet, and the curvature happens in 4 dimensions, not 2. But the essential idea is sound. Mass warps the geometry of space itself, and light follows that warped geometry. So if a massive cluster of galaxies sits between us and a more distant galaxy, the light from that distant galaxy gets bent around the cluster, like a lens focusing light. Sometimes, it creates multiple images of the same background galaxy, stretched into graceful arcs and rings, what astronomers call Einstein rings. If you could see one, it would look like a bright smudge surrounded by a halo of distorted ghost images, each one a different copy of the same far-off galaxy, its light arriving by a different curved path. It's gorgeous, and it's also a weighing scale. By measuring how much the light bends, you can calculate exactly how much mass is doing the bending. And when astronomers do that calculation, the mass they infer from the lensing is, once again, far greater than the mass they can see. The invisible mass is there, bending space-time, shaping the paths of photons that have traveled billions of years to reach our telescopes. You can't see the dark matter itself, but you can see its fingerprints written in light. And then there's the bullet cluster. If I could show you only one piece of evidence for dark matter, one observation, one data set, one image, it would be this one. This is, in a lot of ways, the smoking gun, the piece of evidence that's hardest to explain away. And the story behind how it became so important is a wonderful example of science in action. The bullet cluster. Its proper name is 1E065756, because astronomers are terrible at naming things, is actually two clusters of galaxies that collided with each other. Picture two enormous swarms of galaxies, each containing hundreds of galaxies and vast clouds of hot gas, barreling toward each other at about 10 million miles per hour. This collision has been playing out over the course of roughly 100 million years, which sounds like a long time, but in cosmological terms, it's a snapshot. When two galaxy clusters slam into each other, the individual galaxies pass through mostly unscathed, because galaxies are mostly empty space. They're like throwing two handfuls of bees at each other. The bees just pass through the gaps between other bees. But the hot gas that fills the space between galaxies within each cluster, that gas does collide. It slams together, heats up, and slows down, piling up in the middle of the collision zone. You can see this gas in X-ray observations. It glows brilliantly in X-rays because it's been heated to tens of millions of degrees. So now you have a situation where the visible gas, which is actually the majority of the normal matter in a galaxy cluster, far outweighing the stars, has been slowed down and left in the middle. But where's the gravitational mass? If most of the mass were in the gas, the center of gravity should be where the gas is, in the middle. But gravitational lensing measurements show something different. The center of mass has kept moving. It passed right through the collision, along with the galaxies themselves, as if the collision didn't happen. The dark matter, whatever it is, didn't interact with the gas. It didn't slow down. It didn't pile up. It just kept going, carrying most of the mass with it. The gravitational lensing maps show two clumps of mass, one on each side of the collision, separated from the gas in the middle. This is almost exactly what you'd expect if most of the mass were made of something that doesn't interact with normal matter except through gravity. It passes right through. It doesn't collide. It doesn't feel the electromagnetic force that makes gas slam into gas. It just gravitates and keeps moving. The bullet cluster is stunning because it's so hard to explain without dark matter. You can modify gravity all you want, but the gravitational center shouldn't separate from the gas unless there's actual mass, real stuff, real particles, that's somewhere else. The mass and the light are in different places. That's the signature of invisible matter, and there's still more. Some of the most precise evidence comes from a completely different place, not from galaxies or clusters at all, but from the oldest light in the universe. It's called the cosmic microwave background, or CMB, and it's the faint afterglow of the Big Bang itself, and it has a wonderful discovery story. In 1965, two radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were trying to use a large horn-shaped antenna for radio astronomy experiments, but they kept picking up a persistent low-level noise that they couldn't get rid of. It came from every direction in the sky. It didn't go away at night. It didn't go away when they pointed the antenna in different directions. They even cleaned pigeon droppings out of the antenna, thinking that might be the source. It wasn't. What they were hearing, what they literally couldn't stop hearing, was the remnant radiation from the birth of the universe itself, the cosmic microwave background. It earned them the Nobel Prize. Here's what the CMB actually is. About 380,000 years after the Big Bang, the universe cooled down enough for atoms to form for the first time. Before that moment, the universe was a hot, dense fog of charged particles, protons and electrons, and light couldn't travel freely because it kept scattering off those particles. But the instant atoms formed, the fog cleared, and light was released in every direction. That light has been traveling through space for about 13.8 billion years, stretching as the universe expands, cooling from a blinding white-hot glow down to faint microwave radiation, just a few degrees above absolute zero. And we can still detect it from every direction in the sky with incredible precision. The CMB isn't perfectly uniform. It has tiny ripples in it, variations in temperature and density that correspond to the seeds of all the structure in the universe today. The slightly denser spots in the CMB are where matter was beginning to clump together, and those clumps would eventually become galaxies, galaxy clusters, and the great cosmic web. And here's where dark matter enters the picture. The pattern of those ripples, their sizes, their spacing, their relative amplitudes, depends very sensitively on the composition of the universe. How much normal matter? How much dark matter? How much dark energy? When physicists model those ripples, they find that the observed pattern matches a universe that is about 5% normal matter, about 27% dark matter, and about 68% dark energy. If you remove the dark matter from the model, the predicted ripple pattern looks completely wrong. The peaks are in the wrong places. The relative heights are off. The whole thing falls apart. The dark matter had to be there, influencing how matter clumped in the early universe, for the CMB to look the way it does. And let me add one more layer to this, because it connects to something you can almost feel from where you're lying right now. We are, in a very real sense, a product of dark matter, not made of it. Your body is ordinary matter, atoms, the 5%. But without dark matter, you wouldn't be here. In the early universe, ordinary matter alone couldn't have clumped together fast enough to form galaxies. Regular matter interacts with light. It gets pushed around by radiation pressure. It heats up and smooths out. Dark matter doesn't have that problem. It doesn't interact with light. It isn't pushed around by radiation. So in the early universe, dark matter clumped first. It fell together under its own gravity, forming vast invisible halos and filaments. And then, ordinary matter fell into those dark matter structures, like water pooling in valleys that had already been carved. The dark matter built the scaffolding, and the ordinary matter settled into it, like snow collecting in the crevices of a mountainside. Without that scaffolding, galaxies wouldn't have formed when they did. Stars wouldn't have ignited. Planets wouldn't have coalesced. And you and I wouldn't be having this conversation. The time scale matters here. The universe is about 13.8 billion years old. If dark matter hadn't been there to speed up the clumping process, the first galaxies would have taken much, much longer to form, if they formed at all. Ordinary matter on its own, buffeted by radiation pressure and its own thermal energy, clumps slowly. Dark matter, immune to radiation pressure, clumps quickly. It's the difference between trying to build a sandcastle in a windstorm versus building one in a calm room. The dark matter provides the calm. It creates the gravitational wells where ordinary matter can settle down and start the slow process of becoming stars, planets, and eventually, improbably, living things. The invisible hand of dark matter shaped the conditions for your existence. You owe your life, in a very real sense, to something you will never see, so let's take stock. We know dark matter is real because of galaxy rotation curves, because of the dynamics of galaxy clusters, because of gravitational lensing, because of the bullet cluster, because of the cosmic microwave background. because of the way galaxies formed in the early universe, because of the large-scale structure of the cosmos. These are independent lines of evidence, observed with different instruments, using different techniques, spanning different eras of cosmic history, and they all agree. Something is out there, something heavy, something that gravitates but doesn't shine, doesn't reflect, doesn't absorb, doesn't scatter light. Something that makes up the majority of all the matter in the universe. But what is it? And this is where the story shifts from detection to mystery. Because knowing that dark matter exists is very different from knowing what it is. And despite almost a century of knowing it's there, we still don't know what dark matter is made of. We have ideas. We have candidates. We have some truly brilliant theories. But we have no confirmed answer. Let me walk you through the main possibilities, one by one, and tell you why each is compelling and why each has its challenges. And let me start with the simplest idea of all, the one that turns out to be wrong, but wrong in an instructive way. The first thing you might think is, well, maybe dark matter is just ordinary matter that happens to be dark. Not glowing, not emitting light, but still made of the same protons, neutrons, and electrons that make up everything else. Think about it. There are lots of things in space that are hard to see. Brown dwarfs, for instance. These are objects that are too small to sustain hydrogen fusion, so they never become proper stars. They're dim, cool, and incredibly hard to spot. Or rogue planets. Planets that have been ejected from their solar systems and wander through interstellar space, invisible to most telescopes. Or dead stars, white dwarfs that have cooled to near invisibility, neutron stars, even black holes. All of these are made of ordinary matter, and all of them are hard to see. Collectively, astronomers grouped these hypothetical dark objects under the whimsical name MACHOs, massive astrophysical compact halo objects. And for a while, this seemed like it could work. Maybe the galaxy halos were just full of dim objects we hadn't spotted yet. But the evidence against MACHOs as the primary component of dark matter is now overwhelming, and it comes from several directions. First, there's Big Bang nucleosynthesis. In the first few minutes after the Big Bang, the universe was hot and dense enough for nuclear fusion to occur. Not inside stars, but everywhere, all at once. Protons and neutrons fused together to form the lightest elements, hydrogen, helium, and tiny amounts of lithium and deuterium. The exact ratios of these elements depend very sensitively on how much ordinary matter, baryonic matter, to use the technical term, the universe contains. And when we measure those primordial abundances and compare them to the predictions, we get a very clear answer. Ordinary matter makes up about 5% of the universe's energy budget. That's it. There simply isn't enough baryonic matter in the universe to account for the dark matter, no matter how dim and hard to see it might be. There were also direct searches. Astronomers conducted surveys looking for MACHOs in the halo of our galaxy, using a technique called gravitational microlensing. The idea is that if a compact dark object passes between us and a distant star, its gravity will momentarily bend and magnify the star's light, creating a brief brightening event. Two major surveys, the MACHO project and the EROS project, monitored millions of stars for years, looking for these events. They found some, but nowhere near enough to account for the missing mass. MACHOs exist, but they're a minor component, not the answer. There's something else that argues against MACHOs too, and it's elegant. If dark matter were made of ordinary atoms, baryonic matter, then it would have participated in the nuclear reactions in the first minutes after the Big Bang, and the primordial abundances of hydrogen, helium, and deuterium would be different from what we observe. The numbers are very precise on this. The amount of deuterium in the universe, in particular, is extraordinarily sensitive to the total amount of baryonic matter, and the observed deuterium abundance tells us, flatly, that baryonic matter can't be more than about 5% of the total. Whatever the other 27% is, it's not made of protons and neutrons. So dark matter isn't ordinary matter hiding in the shadows. It's something else, something genuinely new, something not made of protons and neutrons at all. And that's a staggering realization when you sit with it. Let it land for a moment. It means that the particles in the standard model of physics, the framework that describes every particle and every force we've ever directly detected, are not enough. There's an entire category of matter, making up the majority of all matter in the universe, that the standard model doesn't include. Whatever dark matter is, it's beyond what we currently know. Now, the standard model is an astonishingly successful theory. It's one of the greatest achievements of human thought, right up there with general relativity, evolution by natural selection, and the germ theory of disease. It describes 3 of the 4 fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, and catalogs every known elementary particle: 6 quarks, 6 leptons, the force-carrying gauge bosons, and the Higgs boson. It has predicted the existence of particles before they were discovered: the top quark, the tau neutrino, the W and Z bosons, and most spectacularly, the Higgs boson, which was predicted in 1964 and finally found at the Large Hadron Collider in 2012, almost 50 years later. It has been tested to mind-boggling precision. The magnetic moment of the electron, a measure of how strongly the electron interacts with magnetic fields, has been measured to about 13 decimal places and agrees with the standard model's prediction to about 10 of those. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. In the world of physics, the standard model is the gold standard, and yet it has nothing to say about dark matter. Nothing, not a whisper, not a hint. The standard model is a theory of the visible universe, and it does that job magnificently. But it's silent about the invisible majority. That tells you something profound. Whatever dark matter is, its existence is evidence that our understanding of particle physics is incomplete. There are particles out there, maybe entire families of particles, an entire dark sector, that we haven't found yet. So what might those particles be? Let's talk about the leading candidates. The one that has dominated the conversation for the longest time is the WIMP, the weakly interacting massive particle. The name tells you the 2 key properties. It's massive, not as in physically large, but as in it has a significant rest mass, probably somewhere between a few times and a few thousand times the mass of a proton. And it interacts weakly, both in the colloquial sense that it barely interacts with ordinary matter at all, and in the more specific sense that it might interact through the weak nuclear force, one of the 4 fundamental forces. The appeal of WIMPs goes beyond just fitting the bill. There's something called the WIMP miracle, and it's genuinely one of those moments where a coincidence is almost too perfect to be an accident. Here's the idea. In the very early universe, when temperatures were incredibly high, all sorts of particles were being created and destroyed constantly. Particles and antiparticles would pop into existence, collide, annihilate each other, and the energy would create new particles. It was a seething, roiling chaos of creation and destruction. As the universe expanded and cooled, heavier particles stopped being produced because there wasn't enough energy to make them anymore. But they also stopped annihilating each other because the universe had expanded enough that they couldn't find each other anymore. They froze out. And whatever number was left over from that freezing out process is roughly the number we'd see today. Here's the miracle part, and it really is remarkable. So let's take it slowly. If you take a hypothetical particle with a mass in the range of about 100 times the mass of a proton, so roughly the mass of a heavy atom, like a tin atom or a silver atom, and give it an interaction strength roughly equal to that of the weak nuclear force, then you can calculate exactly how many of those particles would have survived from the early universe. You know the temperature history of the universe from the Big Bang model. You know how fast it expanded. You know the relevant physics of particle creation and annihilation. You plug it all in, turn the crank, and out pops a number, the predicted abundance of these hypothetical particles today. And that number matches. It matches almost exactly the amount of dark matter we observe. Not roughly, not within an order of magnitude. It matches with spooky precision. Now, think about what this means. A particle with properties that many theorists were already predicting for completely independent reasons. Reasons having to do with the hierarchy problem in particle physics, which is the puzzle of why the Higgs boson mass is so much lighter than the Planck scale, and the mathematics of supersymmetry, which is a theoretical framework that proposes every known particle has a heavier partner, would automatically, inevitably, produce the right amount of dark matter. Nobody designed it to do this. The particle physicists weren't trying to explain dark matter when they proposed supersymmetry, and the cosmologists weren't thinking about supersymmetry when they measured the dark matter abundance. But the two calculations pointed to exactly the same kind of particle. It was as if two groups of scientists, working on completely different problems in different buildings, both arrived at the same answer, written on a piece of paper slid under the door. It felt like the universe was handing them the answer. And for a good 20 years, from roughly the mid-80s to the mid-2000s, the WIMP was the leading candidate for dark matter, and a lot of very smart people were very confident that it was just a matter of time before one was found. And so the search for WIMPs became one of the great experimental quests in physics. The idea is beautifully simple in principle, even if fiendishly difficult in practice. If WIMPs are passing through the Earth all the time, and they should be, given how weakly they interact, then very rarely one of them might bump into an atomic nucleus in a detector, transferring a tiny amount of energy. Detect that energy, and you've found your dark matter particle. But the word rarely is doing a lot of work in that sentence. We're talking about a particle that can pass through an entire planet without hitting anything. The interaction cross-section, the effective target size of a nucleus, as seen by a WIMP, is unimaginably small. To have any chance of seeing an event, you need a lot of target material, a very long time to wait, and you need to shield your detector from every other possible source of background noise. Cosmic rays, natural radioactivity in the surrounding rock, radon gas, even the radioactive decay of atoms within the detector itself. And that's why dark matter detectors are built deep underground. Think about that for a moment. Scientists have dragged tons of ultra-pure liquid xenon or germanium crystals into the depths of old mines and tunnels, under the Gran Sasso Mountain in Italy, in the Sanford Underground Research Facility in South Dakota. That's in the old Homestake gold mine, nearly a mile down. Inside the Snow Lab in Ontario, 2 kilometers beneath the surface in an active nickel mine, and in the Jinping Laboratory in China, buried under over 2 kilometers of marble. They do this because the rock above acts as a shield, absorbing the cosmic rays that would otherwise swamp the detector with false signals. Try to imagine what that's like. You descend in a cage elevator, dropping through darkness for several minutes. The air changes. The temperature changes. The sounds change. Down there, in the silence and the dark, with the entire weight of a mountain pressing down above them, in clean rooms that rival the most sterile environments on Earth, these detectors sit and wait. They wait for years. They wait for a single atom in their detector to recoil from a collision with something that has no business being there, something that passed through the mountain, through a mile of solid rock, as if it were fog. Because to a dark matter particle, rock is fog. The atoms in the rock are almost entirely empty space, and a particle that doesn't interact through electromagnetism doesn't care about the electron clouds and nuclear charges that make rock feel solid to you and me. It just drifts through, oblivious, as if the mountain weren't there at all. The detectors themselves are marvels of engineering, and I want to spend a moment on them, because they're genuinely astonishing machines. Take the xenon experiment, which has gone through several generations. Xenon 10, Xenon 100, Xenon 1T, and now Xenon T, with ever-increasing sensitivity. Each generation is roughly 10 times more sensitive than the last, which means each one explores territory that no experiment has ever reached before. The current version uses about 8 tons of liquid xenon. Xenon is chosen for several reasons. It's heavy, which makes it a good target for WIMP collisions, because a heavier nucleus absorbs more of the WIMP's kinetic energy in a collision, like a bowling ball being hit by another bowling ball rather than a marble. It's naturally clean. Xenon doesn't have any long-lived radioactive isotopes in significant quantities, so it produces very little background noise on its own, and it scintillates beautifully. When a particle interacts with xenon, the xenon produces a flash of ultraviolet light, a tiny sparkle in the darkness. The xenon is cooled to -95 degrees Celsius, just above its boiling point, and housed in a double-walled cryostat, essentially a thermos for physics, surrounded by a water tank to block stray radiation from the surrounding rock. When a particle interacts with a xenon atom, it produces a tiny flash of ultraviolet light and a small number of free electrons. Both signals are detected by arrays of photomultiplier tubes, incredibly sensitive light detectors, at the top and bottom of the tank. By measuring the timing and pattern of these two signals, scientists can determine where the interaction occurred, how much energy was deposited, and, crucially, whether it was a nuclear recoil, which is what a WIMP would produce, or an electron recoil, which is what background radiation typically causes. The discrimination between these two types of events is extraordinary. These experiments can distinguish between a genuine dark matter signal and a background event with better than 99.5% accuracy. And yet, after decades of searching, with detectors that have grown larger and more sensitive by orders of magnitude, nobody has seen a convincing WIMP signal. Not one. The null results have been piling up for years, pushing the possible interaction strength of WIMPs down and down and down, into territory so faint that the original WIMP miracle is starting to look less miraculous. That doesn't mean WIMPs are ruled out. There's still a wide range of masses and interaction strengths that haven't been fully explored. But the easy versions, the ones that fell naturally out of the simplest supersymmetric models, have been largely excluded. If WIMPs exist, they're hiding in a smaller and smaller corner of the possible parameter space. There's another approach to finding WIMPs too, not waiting for them to come to you, but trying to create them. And this is where the story connects to the most famous physics experiment on Earth, the Large Hadron Collider at CERN, on the border between Switzerland and France. The LHC is a ring of superconducting magnets 17 miles in circumference, buried deep underground, where protons are accelerated to 99.99999% of the speed of light, and then smashed into each other. The energy of these collisions is extraordinary, enough to briefly recreate conditions that haven't existed since a trillionth of a second after the Big Bang. If WIMPs can be produced in such collisions, they would escape the enormous detectors, ATLAS and CMS, each one the size of a cathedral, without interacting, without leaving a trace. And you'd see their signature not as a signal, but as an absence, missing energy, a collision where the outgoing particles don't quite balance the incoming ones, because something invisible carried off some of the energy and momentum. It's like watching a billiard ball collision where the cue ball hits the rack and the colored balls scatter in every direction. But the momentum doesn't add up, which means something you can't see must have flown off carrying the missing momentum. The LHC has been searching for exactly this kind of signal for over a decade, and while it hasn't found WIMPs yet, the searches have placed important constraints on what kinds of WIMPs could exist. They've closed off large swaths of theoretical parameter space, which is progress, even though it's the frustrating kind of progress that tells you what the answer isn't, rather than what it is. There's also a third approach, indirect detection, and it's beautifully complementary to the other two. The idea is this: if WIMPs are their own antiparticles, as many models predict, then wherever dark matter is dense enough, in the cores of galaxies, in dense clumps orbiting within galactic halos, maybe even in the center of the sun, where dark matter particles could accumulate over billions of years, WIMPs should occasionally find each other and annihilate. And when matter and antimatter annihilate, they produce energy in the form of ordinary particles that we could detect: gamma rays, neutrinos, positrons, antiprotons. The Fermi Gamma Ray Space Telescope, orbiting overhead right now as you lie there, has been scanning the sky in gamma rays since 2008, looking for exactly these annihilation signals. The Alpha Magnetic Spectrometer, mounted on the International Space Station, has been measuring cosmic ray antimatter, positrons and antiprotons, searching for an excess that could come from dark matter annihilation in the galaxy. And neutrino telescopes like IceCube, buried in a cubic kilometer of Antarctic ice at the South Pole, are looking for high-energy neutrinos from dark matter annihilation in the Sun or the center of the Earth. There have been some tantalizing hints. An unexplained excess of gamma rays from the center of our own Milky Way, detected by Fermi, has been debated for over a decade. An excess of positrons in cosmic rays, measured by both Pamela and AMS, has generated enormous excitement and equally enormous controversy, but nothing definitive. Every signal that initially looked like dark matter has eventually turned out to be explainable by other, more mundane astrophysical processes: pulsars, supernova remnants, the messy complexity of the galactic center. The universe hasn't made it easy, so if not WIMPs, then what? Let me introduce you to another candidate, one that has been steadily gaining attention and enthusiasm in the physics community over the past decade or so. It's called the axion, and its story is one of the most elegant in all of theoretical physics, because the axion wasn't invented to explain dark matter at all. It was invented to solve a completely different problem, and then, almost as a bonus, it turned out to be a perfect dark matter candidate. The problem the axion was invented to solve is called the strong CP problem. Here's the gist. The strong nuclear force, the force that holds quarks together inside protons and neutrons, and holds protons and neutrons together inside atomic nuclei, is described by a theory called quantum chromodynamics, or QCD. The equations of QCD contain a parameter, a number you can plug in, that, if it were anything other than extremely close to zero, would cause the neutron to have a measurable electric dipole moment. In plain language, the neutron would be slightly positive on one end and slightly negative on the other, like a tiny bar magnet but for electric charge. We've measured this with incredible precision, and the neutron's electric dipole moment is essentially zero. That means this parameter in the QCD equations must be ludicrously small, smaller than about 10 to the minus 10. Now, there's no reason in the standard model for this number to be so small. It could, in principle, be anything between 0 and about 6.3. The fact that it just happens to be almost exactly 0 seems like a bizarre coincidence. It's what physicists call a fine-tuning problem, a situation where a number in your theory has to be very precisely set for things to work, and you have no explanation for why it takes that value. It's like walking into a room and finding a pencil balanced perfectly on its tip. It's possible, but it screams for an explanation. In 1977, two physicists, Roberto Peccei, an Italian-Brazilian theorist, and Helen Quinn, an Australian-American physicist, proposed one of the most elegant solutions in the history of particle physics. They introduced a new symmetry into the equations, what's now called Peccei-Quinn symmetry, that dynamically forces that troublesome parameter to be zero. It doesn't set it to zero by hand. It makes zero the natural value, the way a ball naturally rolls to the bottom of a bowl. The parameter relaxes to zero on its own, driven by the dynamics of the theory. The unwanted CP violation is automatically eliminated. It's elegant, it's economical, and it solves the problem. But as Frank Wilczek and Steven Weinberg independently pointed out shortly afterward, this new symmetry comes with a side effect. When you break a symmetry in quantum field theory, you get a new particle, a light, feebly interacting particle that Wilczek whimsically named the axion after a brand of laundry detergent because it cleaned up a problem in physics. And here's where it gets beautiful. Axions, if they exist, would have been produced copiously in the early universe, not through thermal processes like WIMPs, but through a different mechanism involving the coherent oscillation of the axion field. You can think of it as the axion field throughout the universe, getting stuck in a particular configuration during a phase transition, and then oscillating around its minimum like a ball rolling back and forth at the bottom of a bowl. Those oscillations behave, collectively, as a very cold, very smooth sea of dark matter particles. And the predicted abundance matches. If the axion has a mass in a certain range, roughly between about a microelectron volt and a millielectron volt, you get the right amount of dark matter. Once again, a particle proposed for completely independent theoretical reasons turns out to produce exactly the right amount of dark matter. It's another kind of miracle, though a different one from the WIMP miracle. The catch is that axions are incredibly light, 1,000,000 times lighter than an electron, maybe more, and they interact with ordinary matter even more feebly than WIMPs do. Finding them requires a completely different experimental strategy. The most promising approach exploits a peculiar property of axions. In the presence of a strong magnetic field, an axion can convert into a photon. Just one axion, silently passing through a powerful magnet, can spontaneously become a microwave photon. If you build a microwave cavity, a carefully tuned resonant chamber, and put it inside a powerful magnet, you can try to detect those converted photons. The Axion Dark Matter Experiment, ADMX, at the University of Washington, has been doing exactly this for years. It uses a superconducting magnet and an extremely sensitive microwave receiver, cooled to temperatures colder than outer space, to search for the faint whisper of axion to photon conversion. And because you don't know the exact mass of the axion, you have to tune the cavity to different frequencies and listen at each one, slowly scanning through the possible mass range. It's like tuning an old radio dial through pure static, listening for a faint signal that might be hiding at any frequency. ADMX has reached the sensitivity needed to detect certain axion models and is continuing to push deeper into the parameter space. Other experiments, Haystack, Organ, MadMax, and others around the world, are taking complementary approaches, covering different mass ranges and using different detection techniques. There's something almost poetic about the axion search, and I want to linger on it for a moment, because I think it captures something essential about what it means to do physics at the frontier. You're sitting in a laboratory, surrounded by one of the strongest magnets ever built, a superconducting solenoid producing a field tens of thousands of times stronger than Earth's, and you're listening for the universe to whisper a single photon into your detector. The signal you're looking for is about a billionth of a watt. To put that in perspective, the light from the faintest star you can see with your naked eye delivers about 1 billion times more power to your eyeball than the signal these experimenters are hunting. Your detector has to be colder than deep space. The AtomX experiment operates at temperatures of about 100 millikelvin, which is 1/10 of a degree above absolute zero, colder than anything in the natural universe, except perhaps the deepest voids of intergalactic space. It has to be quieter than the quantum vacuum itself, because at these energy scales, the random jiggling of atoms, the thermal noise of the equipment, even the quantum fluctuations of the electromagnetic field produce more noise than the signal you're hunting. The experimenters use quantum-limited amplifiers, devices that exploit the principles of quantum mechanics to reach the absolute theoretical minimum of noise allowed by the laws of physics. They can't do better. The universe won't let them. And yet, even at this limit, the signal is barely there. The fact that we can even attempt this, that human beings have built machines sensitive enough to listen for a single photon produced by the conversion of a hypothetical particle in a magnetic field, is a testament to the extraordinary ingenuity of experimental physicists. These people are, in a very real sense, building the most sensitive ears ever constructed and pointing them at the universe and asking it to speak. But let me tell you about some of the other candidates too, because the landscape of dark matter possibilities is broader than just WIMPs and axions. And this is where the story takes on the quality of a mystery novel with multiple suspects, each one plausible, each one with an alibi you can't quite verify, and none of them caught red-handed. There are sterile neutrinos, for instance. And to understand what a sterile neutrino is, you first need to appreciate how strange regular neutrinos are. Neutrinos are the ghosts of the particle world. They're produced in nuclear reactions, in the sun's core, in nuclear reactors, in supernovae, in the upper atmosphere when cosmic rays hit. The sun alone produces about 2 × 10⁻38 neutrinos every second. They pour through everything. About 65 billion solar neutrinos pass through every square centimeter of your body every second, day and night, and you never notice a thing. A neutrino can pass through a light year of solid lead with only about a 50% chance of hitting anything. They're that ghostly. Regular neutrinos come in 3 types, or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. All 3 are incredibly light and interact only through the weak force and gravity. But some extensions of the Standard Model predict a 4th type, a sterile neutrino, that doesn't interact through any of the Standard Model forces. It would interact only through gravity and through mixing with the other neutrino types, a quantum mechanical effect that could cause it to occasionally transform into one of the familiar flavors. If sterile neutrinos have the right mass, roughly in the kilo-electron-volt range, they could constitute the dark matter. They would be warm dark matter rather than cold, meaning they would have been moving at moderate speeds in the early universe, which would affect the formation of the smallest structures in the cosmos. There have been some suggestive signals. An unexplained X-ray line at about 3.5 kilo-electron-volts detected from galaxy clusters and the center of the Milky Way that could be the signature of decaying sterile neutrinos. But subsequent observations have given conflicting results, and the matter remains unresolved. And then there are the really exotic possibilities. Primordial black holes are one of the most fascinating. These are black holes that formed not from collapsing stars, the way most black holes form today, but from extreme density fluctuations in the very early universe, in the first fraction of a second after the Big Bang. Back then, the universe was so dense and so hot that even small variations in density, the cosmic equivalent of ripples on a pond, could, if they were large enough, collapse under their own gravity and form black holes. Not stellar mass black holes, necessarily. These primordial black holes could have been any mass at all, from tiny ones lighter than a grain of sand, which would have evaporated long ago through Hawking radiation, to ones as massive as mountains, or moons, or even larger. If enough such black holes formed, with masses in the right range, they could constitute the dark matter, and they'd be perfect candidates in some ways. They don't emit light, they interact only through gravity, and they're stable. They're not a new kind of particle. They're just gravity, doing what gravity does. This idea has gone through cycles of popularity. Some mass ranges have been ruled out by gravitational lensing surveys and other constraints, but there remain windows, particularly around asteroid mass black holes, roughly 10 to the 17 to 10 to the 23 kilograms, where primordial black holes could potentially account for all the dark matter. The detection of gravitational waves by LIGO has added new fuel to this discussion, because some of the merging black holes LIGO has observed have properties that are slightly unexpected if they formed from stellar evolution, but would be natural if they were primordial. There's even the possibility of an entire dark sector, and this is one of those ideas that, once you hear it, you can't quite shake. A whole zoo of dark particles, with their own forces and interactions, that simply don't couple to our particles except through gravity, and possibly through some tiny, feeble portal interaction that we haven't detected yet. Think about it. Our visible world has 6 types of quarks, 6 types of leptons, force-carrying bosons, the Higgs. That's a rich, complicated ecosystem of particles and forces, all interacting with each other in intricate ways. Why should the dark sector be simple? Why should 27% of the universe be just one boring particle, with no internal structure and no interactions other than gravity? Maybe dark matter particles interact with each other through a dark force, mediated by a dark photon. Maybe there's a dark chemistry, dark atoms, dark molecules. This might sound like wild speculation, but it's taken seriously by theorists, and there are experimental consequences. Certain types of dark forces would leave detectable imprints on the dynamics of galaxy collisions, or the distribution of dark matter within halos. And here I want you to pause and appreciate just how strange the landscape of possibilities has become. We started this whole story with Fritz Zwicky noticing that galaxy clusters were moving too fast. The simplest explanation was extra mass, dark matter. And now, almost a century later, the candidates range from particles heavier than atoms to particles lighter than a billionth of an electron volt, from microscopic black holes to entire hidden sectors of reality with their own forces and chemistry. The range of what dark matter could be spans more than 60 orders of magnitude in mass. That's like saying the answer could be an ant, or it could be a galaxy, and you have to figure out which one. The fact that we can still narrow it down, that experiments are actually making progress, is remarkable. Let me take you on a slight tangent here, because I think it enriches the picture. There is an alternative to dark matter that I mentioned earlier, and it's worth spending some time on. It's called MOND, Modified Newtonian Dynamics, and it was proposed in 1983 by an Israeli physicist named Mordechai Milgrom. Milgrom's idea was radical and simple. Maybe there is no dark matter. Maybe what we're seeing is that Newton's law of gravity, and by extension, general relativity, doesn't work quite right at very low accelerations. In your everyday life and everywhere we've tested gravity directly, accelerations are relatively high, but at the outskirts of a galaxy, where stars are orbiting slowly in the faint gravitational field of the distant galactic center. The accelerations are incredibly tiny, about 10 to the minus 10 meters per second squared. Milgram proposed that below a certain critical acceleration threshold, gravity behaves differently. It doesn't fall off as fast with distance as Newton's law predicts. Instead, it falls off more slowly, which means the outer parts of galaxies experience stronger gravitational pull than Newton would predict, which means they orbit faster, which means the rotation curves come out flat without any dark matter at all. And here's the remarkable thing. MOND works astonishingly well for individual galaxies. It predicts galaxy rotation curves with extraordinary accuracy, often using a single parameter for all galaxies. Where dark matter models need to adjust the amount and distribution of dark matter for each galaxy individually, MOND uses one universal number and gets them all right, or close to right. For some people, this is deeply impressive. The fact that one simple modification to gravity can reproduce what dark matter models need extensive fine-tuning to achieve is, at the very least, a clue that something interesting is going on. There's something almost unsettling about how well MOND works for galaxies. It predicts a relationship, called the radial acceleration relation, between the gravitational acceleration you'd expect from the visible matter alone and the acceleration you actually observe. This relationship holds across galaxies of wildly different sizes, luminosities, and morphologies, with remarkably little scatter. It's a tight empirical law, and dark matter models have to work quite hard to reproduce it. That doesn't mean MOND is right, but it does mean MOND is telling us something. There's a pattern in the data that our dark matter models need to explain. But MOND has serious problems at larger scales. It doesn't work well for galaxy clusters. There's still missing mass even after you apply the MOND correction. It struggles with the bullet cluster, where mass is clearly separated from the visible gas, and it has a very hard time reproducing the detailed pattern of ripples in the cosmic microwave background, which the dark matter model predicts with remarkable precision. Most physicists today regard MOND not as the whole answer, but possibly as an empirical clue, pointing towards something deeper, perhaps a more fundamental theory that naturally produces MOND-like behavior at galactic scales, while also incorporating dark matter at larger scales. Some theories along these lines do exist. It's an active area of research, and the debate isn't over. Now, I want to bring you back to the direct search for dark matter, because the story of these experiments is one of the most dramatic in modern physics. Imagine spending years building a detector of unprecedented sensitivity, shielding it from every conceivable source of background noise, carefully calibrating every component, commissioning it, running it, collecting data, analyzing the data with exquisite statistical rigor, and finding nothing, absolutely nothing. Just the quiet hiss of background events, all of them accounted for by known physics. And then you publish your result. We did not find dark matter. Here is our new upper limit on the interaction cross-section. And then you start building a bigger, more sensitive detector. And you do it all again. This is what the dark matter direct detection community has been doing for 3 decades. Each new generation of experiments pushes the sensitivity down by about an order of magnitude. Xeon 1T gave way to Xeon NT. Lux gave way to Lux Zeppelin, or LZ. Panda X in China is competing stride for stride. These experiments now probe interaction cross-sections that are almost inconceivably small, about 10 to the minus 47 square centimeters, for a WIMP mass of 30 times the proton mass. That number is so small, it's hard to even convey what it means. It means that a dark matter particle could pass through a wall of lead, a light year thick, and still have a decent chance of making it through without hitting anything. And yet there's a floor, a limit to how far down these experiments can push. It's called the neutrino fog, or the neutrino floor. At some point, the detectors become so sensitive that they start seeing coherent scattering of neutrinos off atomic nuclei, solar neutrinos, atmospheric neutrinos, supernova neutrinos. These neutrino interactions produce signals that look very similar to what a WIMP interaction would look like. And neutrinos are not dark matter. They're ordinary standard model particles. But they create an irreducible background that makes WIMP detection much harder. We're not quite at the neutrino floor yet, but the next generation of experiments will approach it, and going beyond it will require entirely new strategies. Let me pause for a moment, because I think this part of the story deserves some quiet attention. Think about the sheer stubbornness this requires. The experimental dark matter community has been searching for decades without a positive detection. The parameter space they've excluded is vast. The easy answers have been ruled out. The remaining possibilities are increasingly difficult to reach, and yet they keep building, keep pushing, keep refining. This is science at its most tenacious. These are people who have dedicated their careers, their entire professional lives, to listening for a signal that may never come. That takes a kind of faith, not in the religious sense, but in the scientific sense, a conviction that nature has an answer, that the question is well posed, and that the answer is findable if you're clever enough and patient enough and willing to build a detector big enough and quiet enough. There's a wonderful quote from Vera Rubin that captures this spirit. She said, "In a spiral galaxy, the weights of the stars that we observe aren't nearly enough to hold the galaxy together. So if Newton's law holds at great distances, then there is a lot of unseen matter in galaxies." And then she added, "I believe all of the matter is real." She wasn't hedging. She wasn't saying maybe. She was saying, the evidence is clear. The matter is real. Go find it. And that's what people are doing. Right now, as you're lying here, in labs around the world, detectors are running. In the Gran Sasso National Laboratory, a mile under the Apennine Mountains in Italy, tons of liquid xenon are sitting in the dark, watched by hundreds of light sensors, waiting for a nudge that would change everything. In Lead, South Dakota, in a former gold mine nearly a mile underground, the LZ experiment is doing the same. In the Jinping Underground Laboratory in Sichuan Province, China, the deepest underground lab in the world, shielded by nearly 8,000 feet of marble, Panda X is listening. And at the University of Washington, inside a superconducting magnet, ADMEX is scanning for the faint microwave whisper of an axion converting into a photon. Let me tell you about one more experimental frontier, because it's one of the newest and most creative. Some physicists have started to wonder whether dark matter might be much lighter than WIMPs. Not just lighter like axions, which are very light, but ultralight. Fuzzy dark matter, it's sometimes called, because if dark matter particles were light enough, their quantum wavelength would be astronomically large, comparable to the size of a small galaxy. This would give dark matter a fundamentally wave-like character on the scales of galaxy cores, smoothing out the small-scale structures that cold dark matter simulations predict, but observations don't always confirm. It's an intriguing idea, though it comes with its own challenges and constraints. And this is where the story of dark matter detection enters what I think of as its renaissance. There are tabletop experiments now, small, precise, and extraordinarily clever, looking for dark matter in ways that the big underground detectors can't. Where the xenon and germanium experiments excel at finding heavy particles like WIMPs, these new experiments are designed to find much lighter particles, particles so light that they can't kick a heavy nucleus hard enough to detect, but might disturb something smaller and more delicate. Mechanical sensors that can detect the tiny vibrations caused by a dark matter particle bumping into a crystal lattice. Superconducting devices that can sense the minuscule amount of energy deposited by a single interaction. Quantum sensors that exploit the weirdest features of quantum mechanics to push sensitivity beyond classical limits. The field is diversifying, spreading out, exploring every corner of the parameter space. The old certainty that dark matter is a wimp has given way to a broader, more creative, more open-minded search. But why is it so hard to find? Why, after all these experiments, all these years, all this effort, has dark matter remained invisible? Part of the answer is simply that dark matter interacts incredibly weakly. That's what makes it dark. But there's a deeper reason too, and it has to do with how we detect things in general. Think about what it means to see something. Your eyes detect photons, particles of light, that bounce off objects or are emitted by them. Your ears detect sound waves, pressure waves, in air. Every instrument we've ever built ultimately relies on some interaction between the thing being detected and the detector itself. And dark matter, by definition, barely interacts with normal matter. It doesn't emit photons. It doesn't absorb photons. It doesn't interact through the electromagnetic force at all, which means it's invisible to everything that relies on electromagnetism, which is essentially everything in chemistry, biology, and everyday physics. It doesn't feel the strong nuclear force. It may or may not interact through the weak force, and if it does so at a level that's right at the edge of, or below, our current ability to measure. Dark matter is elusive not because we're not looking hard enough, but because it's playing a fundamentally different game than the matter we're used to. It lives in a different sector of reality, connected to us almost exclusively by gravity. And gravity is by far the weakest of the four fundamental forces. At the scale of individual particles, gravity is about 10 to the 36th times weaker than electromagnetism. Trying to detect individual dark matter particles through their gravitational interaction is utterly hopeless with any foreseeable technology. So we're left looking for whatever feeble non-gravitational interaction dark matter might have. Some tiny coupling to ordinary matter, some residual connection to the standard model, and hoping it's large enough to measure. And here's a thought that might blow your mind a little bit, even as you're drifting off. Right now, as you lie there, something like 100 billion neutrinos from the sun pass through every square centimeter of your body every second. You never feel them. They pass through the entire Earth and come out the other side without slowing down. And yet, neutrinos are sociable compared to dark matter. Neutrinos at least interact through the weak force. Dark matter may not even do that. Dark matter particles may be passing through you right now in even greater numbers, and the probability of even one of them interacting with one of the atoms in your body during your entire lifetime is essentially zero. You are, quite literally, transparent to the most common type of matter in the universe. And this brings me to something I think is worth dwelling on, because it reveals something important about the nature of knowledge itself. We live in a universe where the vast majority of matter is something we've never directly touched, tasted, or measured. We know it's there. We know roughly how much of it there is. We know how it's distributed. We can map it, weigh it, simulate its behavior. But we've never held it. It's like knowing someone by their shadow. You can see the shape, you can track the movement, you can infer the size and the speed, but you've never seen the face. And that's a profoundly humbling position for a species that has figured out how to split atoms, read DNA, and detect gravitational waves from colliding black holes a billion light-years away. We can do all of that, and we still can't identify the most common type of matter in the universe. Let me come back to the physics, because there's one more thread I want to pull on, and it connects dark matter to some of the deepest open questions in all of science. And I think this thread is particularly fitting for a late-night conversation, because it's about the limits of what we know, the edge of the map, where the known world gives way to mystery. One of the great unsolved problems in physics is the nature of dark energy, the mysterious force, or property of space, or cosmological constant, or something else entirely, that's causing the expansion of the universe to accelerate. This was discovered in 1998 by two independent teams of astronomers studying distant supernovae, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. They expected to find that the expansion of the universe was slowing down, because gravity should be pulling everything back together. Instead, they found that the expansion is speeding up. Something is pushing the universe apart, and it's winning against gravity on the largest scales. Dark energy makes up about 68% of the universe's total energy budget, even more than dark matter. Together, dark matter and dark energy constitute about 95% of the universe's total content, and we don't understand either of them at a fundamental level. Think about that. 95%. We've built a civilization, decoded DNA, split atoms, visited the moon, photographed black holes, and 95% of the universe is stuff we can't identify. Some physicists wonder whether they're related, whether there's a unified framework that explains both. Others think they're completely independent phenomena. Nobody knows. And then there's the question of gravity itself. General relativity, Einstein's theory of gravity, is a classical theory. It describes gravity as the curvature of space-time, and it works beautifully at large scales. But at very small scales, at the Planck scale, about 10 to the minus 35 meters, the smooth fabric of space-time should become subject to quantum effects, and general relativity breaks down. We don't have a quantum theory of gravity yet, despite decades of effort. String theory offers one possible framework. Loop quantum gravity offers another. But neither has been experimentally tested, and neither has been shown to be definitely correct. Why does this matter for dark matter? Because dark matter interacts primarily through gravity. If our understanding of gravity is incomplete, and it clearly is, since we can't reconcile it with quantum mechanics, then it's possible that the solution to the dark matter problem lies not in a new particle, but in a new understanding of gravity. Not just a simple modification like MOND, but something deeper, something that emerges from the quantum nature of spacetime itself. This is speculative territory, and I want to be upfront about that. But some physicists, including Eric Verlinde and others, have proposed that dark matter might be an emergent phenomenon, a manifestation of the entanglement structure of spacetime, or of information-theoretic properties of the vacuum. In these pictures, there are no dark matter particles. Instead, what we interpret as the gravitational effects of dark matter is actually gravity itself behaving differently than Einstein predicted, in a way that only a deeper theory could explain. These are beautiful ideas, but they're far from proven. Most of the mainstream physics community still favors the particle explanation, that dark matter is a new type of particle, and we just haven't found it yet. But the fact that these alternative ideas are taken seriously tells you something about the state of the field. We're genuinely uncertain. The answer is not yet in, and the range of possibilities is wide. Let me tell you about one more piece of the puzzle, because I think it's one of the most beautiful. It has to do with the large-scale structure of the universe, the way matter is distributed, not on the scale of individual galaxies, but on the scale of hundreds of millions of light-years. When astronomers map the positions of galaxies across these vast distances, they find an astonishing pattern. Galaxies aren't scattered randomly. They're arranged in a vast web, a cosmic web, of filaments and walls and nodes, surrounding enormous voids where almost nothing exists. The filaments can stretch for hundreds of millions of light years, like the threads of an impossibly vast spider's web. At the nodes where filaments intersect, you find massive clusters of galaxies, and in the voids between them, emptiness stretches for tens or hundreds of millions of light years. This structure is not random, and it's not small. The largest structures in the cosmic web, the great walls and supercluster complexes, stretch for billions of light years. The Hercules Corona Borealis Great Wall, if it's real, would be about 10 billion light years across. That's so large that light from one end wouldn't reach the other end, even if it had been traveling since the Big Bang. The voids between the filaments are similarly enormous. The Boötes void, for instance, is about 330 million light years across and contains almost nothing, a region of space large enough to swallow hundreds of thousands of galaxies, and it's nearly empty. The universe is structured like a sponge at the largest scales, and the pattern is hauntingly beautiful. This structure was seeded by the tiny density fluctuations in the early universe, the same fluctuations that left their imprint on the cosmic microwave background, and the growth of that structure was driven primarily by dark matter. In the early universe, dark matter began to clump under its own gravity, forming the filaments and halos of the cosmic web. Ordinary matter, drawn in by the dark matter's gravity, followed later, eventually forming galaxies within those dark matter halos. The cosmic web is, in a very real sense, the skeleton of the universe, and it's made of dark matter. The galaxies we see, the bright, shining collections of stars, are just the luminous tips of an invisible architecture, computer simulations of cosmic structure formation, like the Millennium Simulation and its successors, Illustris TNG, Eagle, and others, have modeled this process in extraordinary detail. These simulations are among the most computationally intensive calculations ever performed. They track the gravitational interactions of billions of dark matter particles over billions of years of cosmic time, following the formation of structures from the smooth initial conditions of the early universe to the rich, complex cosmic web we see today. They start with a uniform distribution of dark matter, imprinted with the tiny fluctuations predicted by inflation, the rapid expansion of the universe in its first tiny fraction of a second, and let it evolve under the influence of gravity and the expansion of the universe. The resulting structures, the filaments, the voids, the clusters, the halos around individual galaxies, match the observed distribution of galaxies with remarkable fidelity. When you overlay the simulated dark matter distribution with the observed galaxy distribution, they line up. The match isn't perfect. There are some small-scale discrepancies that are actively being investigated, like the missing satellites problem, where simulations predict more small satellite galaxies around galaxies like the Milky Way than we actually observe. But the large-scale agreement is stunning. The cosmic web that we see is the visible trace of a much vaster dark web that we don't see. The galaxies are like city lights seen from an airplane at night. They trace the roads and neighborhoods, but the actual infrastructure, the ground beneath the lights, is invisible in the darkness. And here's something beautiful to think about as you're lying there. You are part of this web. The Milky Way sits within a dark matter halo that extends far beyond the visible galaxy. That halo is connected to the local filament of the cosmic web, which connects to larger structures, which connect to still larger structures, all the way up to the scale of the entire observable universe. Every galaxy, every star, every planet, every person, all of it is embedded in this invisible architecture. You are, quite literally, lying inside a structure made of something you've never seen and can't touch, something that has been shaping the universe since before the first atom formed. I want to tell you one more story before we start to wind down, because it captures something essential about the spirit of this search, the tension between hope and rigor, between wanting to find something and needing to be sure. Starting in the late 90s and continuing through multiple upgrades, an experiment called Gamma-Libra, operating in the Gran Sasso laboratory in Italy, has claimed to detect an annual modulation in their data that could be a dark matter signal. This is one of the most controversial results in all of modern physics, and the debate around it has been running for over 20 years. The idea behind annual modulation is elegant. As the Earth orbits the Sun, and the Sun orbits the center of the Milky Way, the Earth should experience a dark matter wind, a stream of dark matter particles that the Earth is plowing through. In June, when the Earth's orbital velocity adds to the Sun's motion through the galaxy, the wind should be stronger. In December, when the Earth's velocity subtracts from the Sun's, it should be weaker. This would produce a seasonal variation in the rate of dark matter interactions in a detector, more in summer, fewer in winter. Gamma-Libra has been observing exactly this pattern for more than 2 decades, with high statistical significance. They see a clear annual modulation, peaking around June, with exactly the right phase and amplitude. If you take it at face value, it's one of the most important experimental results in all of physics, the first direct detection of dark matter. But here's the problem. No other experiment has been able to reproduce it. Multiple independent experiments, using different detector materials and different techniques, have searched for the same signal and come up empty. Their null results are in tension with Gamma-Libra's claim, meaning that if Gamma-Libra is seeing dark matter, these other experiments should have seen it too, and they haven't. This has led to an ongoing, sometimes heated debate in the community. Could Gamma-Libra be affected by a systematic error, some seasonal variation in background noise, like radon levels or muon rates, that mimics the dark matter signal? Could there be a more exotic explanation that's consistent with both the Gamma-Libra positive result and the other experiment's null results? Several new experiments have been designed specifically to test the Gamma-Libra claim using the same detector material, sodium iodide crystals, to eliminate any material-dependent effects. The Anais experiment in Spain and the Cosine 100 experiment in South Korea are among them, and their results so far have not confirmed Gamma-Libra's signal. This is how science works at the frontier. It's messy, it's contentious. Results disagree. Colleagues debate, sometimes heatedly, sometimes for decades. The answer isn't clean and tidy. It's fought over, inch by inch, experiment by experiment, conference talk by conference talk. And that's okay. That's what makes it real. If the answers came easy, they wouldn't be worth much. The fact that scientists are willing to spend 20 years arguing about a single data set, designing entirely new experiments to test a single claim, and holding each other to the most rigorous standards of evidence, that's not a weakness of the scientific process. That's its greatest strength. The answer, when it finally comes, will have earned every ounce of our trust. So where does all of this leave us? Let me try to bring the threads together. We know dark matter exists. The evidence is overwhelming and comes from multiple independent sources: galaxy rotation curves, galaxy cluster dynamics, gravitational lensing, the bullet cluster, the cosmic microwave background, large-scale structure formation, Big Bang nucleosynthesis. These lines of evidence use different instruments, different techniques, different assumptions, and they all converge on the same conclusion. About 85% of the matter in the universe is something invisible, something that interacts through gravity, but not through electromagnetism or the strong force. We know what dark matter isn't. It isn't ordinary matter hiding in dim objects. Big Bang nucleosynthesis and microlensing surveys have ruled that out. It isn't regular neutrinos. They're too light and too fast to clump into the structures we observe. They'd smooth things out, not clump things up. It isn't an artifact of measurement error or observational bias. The evidence is too consistent, too precise, and confirmed by too many independent methods, using different instruments and different physical principles. And it almost certainly isn't a simple modification of gravity, because modified gravity theories can't explain the full range of observations, especially the bullet cluster and the CMB, without sneaking some form of dark matter back in through the door. We have promising candidates for what it might be. WIMPs remain possible, though the simplest versions are increasingly constrained. Axions are theoretically motivated and experimentally searchable. Sterile neutrinos, primordial black holes, and particles from a hidden dark sector all remain on the table. Each candidate has its own experimental program, its own detection strategy, its own community of passionate researchers. And we have a growing suite of experiments: underground detectors, particle colliders, astrophysical observatories, tabletop experiments, gravitational wave detectors, all converging on the question from different angles. The next decade is going to be transformative. Experiments like Exion AT and LZ will either find a signal or push so deep that they'll reach the neutrino floor, changing the game entirely. ADMEX and other axion experiments will explore the most theoretically motivated axion masses. The Vera C. Rubin Observatory, named, fittingly, after the astronomer who did so much to establish the evidence for dark matter, is a telescope being built in Chile that will photograph the entire southern sky every few nights. Its primary camera has over 3 billion pixels. Over its 10-year survey, it will catalog billions of galaxies and measure the subtle distortions in their shapes caused by the gravitational lensing of intervening dark matter. By analyzing those distortions statistically, what's called weak lensing, astronomers will be able to map the distribution of dark matter across the sky with a detail and completeness that has never been possible before. They'll be able to see how dark matter is distributed in 3 dimensions, how it clumps, how it flows, and how its distribution has evolved over cosmic time. This is the equivalent of finally being able to see the scaffolding, not the building itself, but the framework that holds the building up. The European Space Agency's Euclid mission is designed to do the same from space. Next-generation CMB experiments will refine our measurements of the universe's composition, and future particle colliders, if they're built, could probe entirely new energy ranges for dark matter candidates. But there's a possibility we have to sit with, too. The possibility that the answer isn't what anyone expected, that dark matter isn't a simple particle, that it isn't any of our current candidates, that it requires a revision of physics at a level we haven't yet imagined. The history of science is full of moments like this. Moments where the existing framework is stretched to its breaking point, and something fundamentally new is needed. The ultraviolet catastrophe in classical physics, which led to quantum mechanics. The invariance of the speed of light, which led to special relativity. The perihelion precession of Mercury, which led to general relativity. In each case, the old theory worked beautifully within its domain, but the anomalies pointed toward something deeper. And think about what it would mean if we did find it. If tomorrow, a lab announced the unambiguous detection of a dark matter particle, a clear signal, reproduced by independent experiments, with the particle's mass and interaction strength pinned down, it wouldn't just solve one problem. It would crack open an entirely new chapter of physics. We'd know what 27% of the universe is made of. We'd have our first direct evidence for physics beyond the standard model. We'd have a new particle to study, new interactions to probe, new forces to understand. It could lead to a revolution comparable to the discovery of the electron or the nucleus. It would be one of the biggest scientific discoveries in human history, full stop. Dark matter might be our generation's anomaly, the thing that doesn't fit, the shadow on the wall that tells us our picture of reality is incomplete. And if that's the case, then solving the dark matter problem won't just tell us what one more particle is. It will transform our understanding of the fundamental laws of nature. Let me tell you one more thing before we start to settle into the quiet part of this conversation. There's a concept in physics called the lamppost problem. It comes from an old joke about a person searching for their lost keys under a street lamp, not because that's where they dropped them, but because that's where the light is. The worry, for dark matter, is that we've been looking where we know how to look. Wimps, because they fit neatly into theories we already had. Axions, because they emerge from problems we already understood, rather than where the answer might actually be. Maybe dark matter is something so different from our existing theories that we haven't even imagined the right experiment yet. Maybe it lives in a corner of parameter space that our current technology can't reach. Maybe the answer requires a conceptual leap that hasn't been made. This isn't a counsel of despair. It's actually exciting, if you think about it the right way. It means there might be an entire layer of reality, an entire sector of particles and forces that we haven't even begun to uncover. It means the universe still has surprises for us. Big ones. The kind that change textbooks and rewrite our understanding of what's fundamental. And you know what I find most beautiful about all of this? It's the honesty. The willingness of the scientific community to say, we don't know. Not as a failure, but as a starting point. Every experiment that comes up empty isn't a defeat, it's information. It tells us where the answer isn't, which narrows down where it might be. Every null result sharpens the question, focuses the search, and pushes us closer to the edge of what's knowable. Think about what it means to live in a universe where most of the matter is invisible. It means that when you look up at the night sky, you're seeing the Minority Report. The stars, the galaxies, the nebulae, all of it is just the bright foam on a dark ocean. The real substance of the cosmos is hidden from your eyes, accessible only through its gravitational whisper. And yet that whisper is everywhere. It's in the way galaxies spin. It's in the way light bends around clusters. It's in the temperature ripples of the oldest light in the universe. It's in the very structure of the cosmic web that connects all things across billions of light years. You are lying inside that web right now. The dark matter halo of the Milky Way extends hundreds of thousands of light years in every direction, far beyond the visible disk of stars. Dark matter particles, whatever they are passing through your body at this very moment, millions of them every second, and you will never feel a thing. They are the silent majority, the invisible scaffolding, the hidden architecture of everything. And somewhere, right now, in a lab deep underground, in the cold and the quiet, a detector is waiting for one of those particles to finally, after billions of years of cosmic indifference, interact. To bump into one of our atoms and leave a mark, a tiny flash of light, a slight vibration, a single data point that would change everything we know. Maybe it will happen tonight. Maybe it will take another decade. Maybe the answer will come from a direction no one is looking. But the search continues, carried forward by the same thing that has always driven science, the conviction that the universe makes sense, that the invisible is not unknowable, and that the patience to keep asking is itself a form of understanding. The dark matter is out there. It's in here, too, passing through the walls, through the bed, through you. And even though you've never seen it, never touched it, never felt it, it has shaped everything. Every galaxy you've ever admired, every star you've ever wished on, every atom in your body, all of it was cradled by dark matter's gentle pull, guided into existence by something unseen. You are, in the most profound sense, a child of the dark. And that's a good thought to hold on to as you drift off. That the universe is vaster and stranger and more mysterious than anything you can see with your eyes. That there are truths out there, waiting to be discovered, hidden in the dark spaces between the stars. That the biggest questions aren't the ones we've answered, they're the ones we're still brave enough to ask. And that right now, at this very moment, someone somewhere is sitting in the quiet of an underground laboratory, watching a screen in the dark, hoping for a glimmer, a single photon, a faint nudge, the first word of a message from the invisible universe. Sleep well. The mystery will still be here in the morning. And honestly, I think the universe likes being mysterious. I think it wants us to keep looking, keep wondering, keep marveling at how much we don't know. Because the not knowing isn't emptiness. It's an invitation. And the dark isn't frightening when you understand that it's just the universe keeping its deepest secrets for last. The dark matter is holding everything together. It's holding the galaxies in their shapes, the clusters in their orbits, the cosmic web in its vast, intricate architecture. And in a way, it's holding this moment too, the quiet, the stillness, the space between waking and sleep. Let the mystery be a blanket. Let the questions be a lullaby. And let the thought that 95% of reality is still waiting to be understood make the darkness feel less like an absence and more like a promise. There is so much left to discover, and tomorrow the search goes on. But tonight, you don't need to solve anything. You don't need to understand it all. You just need to know that the universe is large enough and strange enough and generous enough to keep giving us questions worth asking. That's more than enough for one night. The room around you is quiet. The atoms in the walls are humming with their tiny quantum vibrations, held together by electromagnetic forces, their nuclei bound by the strong force, their electrons obeying the strange rules of quantum mechanics. And threading through all of it, through the walls, through the floor, through you, the dark matter drifts, serene and untouchable, the silent partner in the dance of everything. You'll never feel it, but it's there. It has always been there, and somewhere, in the deep quiet of an underground laboratory, the universe is being listened to with an attention and a patience that might be the most beautiful thing human beings have ever done. Listening for a whisper from the dark. Listening for the answer to a question we first asked almost a century ago, lying awake at night, wondering what holds the stars together. Sleep well. The stars are holding. The galaxies are spinning. The dark matter is cradling everything in its invisible arms, and the universe, in its own quiet way, is still telling its story, even now, even here, even as your eyes close and the world fades to something soft and warm and wonderfully, beautifully dark.